At AV&R, our mission is to humanize robotics. We decided to create this podcast series to help you demystify the world of robotics and discover what some of the brightest minds in the field are doing. Welcome to Robotics for All Podcasts by AV&R.
Today we're talking with Bryan Germann, who is product manager of the Optomec aerosol jet product line, including machine platforms, print engine products, as well as digital software products. He is also managing strategic customer projects centered around volume production applications for aerosol jet technology. Bryan joined Optomec mid-2017, where previously worked for GE Power and successfully integrated Optomec's aerosol jet technology into production work cells for printing high-temperature ceramic sensors on heavy-duty gas turbine blades. Today, Bryan and I, we look at a couple European Commission reports. The first one going back to 2017 called The Disruptive Nature of 3D Printing, where they outline some predictions for 3D printing and some of the obstacles, and we compare some notes around where the technology is today. And then we go into their May update, which covers the 3D printing of hybrid components and mentions Optomec. Hope everyone enjoys the show. Here we go. Hi, Bryan. Thanks for joining today. How are you doing?
Doing great. How are you, Mike?
Doing excellent. Yeah, I'm excited to talk with you about some of these reports that we've been sharing and get some of your impressions and talk about some of the new things that are happening. 3D printing has been a topic in our minds for many years, and there's been a lot of interesting press and a lot of promising reports. So it'll be good to hear from you as who's deep in the trenches and working actively on this stuff.
Mm-hmm. Yeah, absolutely.
Okay, so the first time that you and I started working together, that was a few years ago, and it was an additive application. The first thing, when I start looking at the different reports and different videos, people sometimes make a distinction between 3D printing and additive manufacturing. So is there a distinction that you put towards those, and what's the difference?
Yeah, so 3D printing, right? The process of making a three-dimensional object that is layer-wise based printing, what you would normally consider powder bed fusion or fused depositional modeling or SLA. All of those are the kind of the accurate incarnation of 3D printing and additive manufacturing. I mean, I think the difference, what additive manufacturing means is that the component is additively manufactured, right? And that there are a bunch of different printing technologies that fall underneath that. And there are a bunch of even emerging techniques like additively manufactured electronics that are, coming into the space. And I think that's, some of the areas where I focus on a lot, but printing onto surfaces, onto objects, adding features to surfaces is just as much additive manufacturing as printing the entire object out of a certain material. So I think that they're synonymous with each other, and it kind of overlaps. You're going to see new ways of making things both that are coming out now and that will come out in the future that will be enabled by additively manufactured techniques.
Yeah, so you talked a little bit about the circuit board printing. So that is actually the technology where you and I first did a project together. It was around the am I saying it right, the aerosol jet system from Optomec?
Yeah, so aerosol jet, I'm the product manager for aerosol jet, and the process is a printing process just like any other, right? So fused deposition modeling, taking a roll of plastic and pushing it through an extruder. That extruder is effectively a print head. How you integrate it into a machine and manipulate that print head in order to create objects is what makes that capability unique. Otherwise it's just a hot plastic extruder. So what we do is we make a technology called aerosol jet, which is has the ability to create dense aerosols of nanoparticle based materials and deposit them down onto substrates in very unique ways. So this could be anything from printing a circuit onto a three-dimensional object or printing a three-dimensional object out of a unique material. Many of our customers have, created microstructures that, have 10 micron features in them, and they're millimeters tall. So that's kind of the scale that we're dealing with aerosol jet, but it is a additive manufacturing or printing technology that is applied both to electronics, or in the case of the application that you and I were talking about, we were printing ceramics. So we were printing ceramic coatings. It was not, it was just a functional material being printed in a unique way onto an object.
Yeah, and I think that's what captured my imagination the most, was how you guys were printing ceramics that were going onto a part inside of a hot section of a gas turbine. And, I'm coming from my background, that was something I didn't think was possible. I've done a lot of work with, 2D matrix, laser marking and stuff like that. And the minute it goes into a hostile environment, good luck trying to keep that into a functional marking. But with what you guys did and what you're able to pull off with the ceramics is you're going into those hostile environments, and it was what what they call hybrid printing, right? So you're putting a ceramic onto a metal surface and you're doing it with high accuracy. So I thought it was just a phenomenal application, and I always think about, well, how did you guys stumble on that? And I'm always curious about that.
Yeah, so it's kind of interesting. I had the unique pleasure of working with some really great people. Dr. Bill Ranson was my professor in college for statics and engineering, and he imparted wisdom onto me. And when I got close to graduation, I had an opportunity to go and work for his little startup company that he had created, which was essentially a measurement technology for quantifying strain on an object in a field environment. So it was a passive strain indicator. Think of it like a tattoo that you get, when you're young. It's kind of normal shaped, and as you get older, it stretches, and that tattoo is a little bit of an indication as to how old you are. It's kind of the same thing, but with parts, right? So we initially started with traditionally 2D polyimide back strain gauge type geometries, where we would, create these patterns onto a piece of plastic, and we would glue them onto the surface of a plane or a bridge. And we would periodically go out and inspect those sensors, and it would detect whether or not there was a crack forming or how much strain was in the material that was underneath it. That was the whole concept. But my professor had another graduate student that happened to work at General Electric, and he basically looked at the technology and said, if you ever figure out how to get that into the hot gas path section at over 2,000 degrees Fahrenheit for very long periods of time, call me, because GE would be very interested in being able to do that. And we started playing around with some refractory ceramics and different approaches to making it, and that led us to aerosol jet, and as an application technology for being able to print these materials. And solid oxide fuel cells is actually where the underlying ceramics themselves came from. And all those pieces culminated into applying the technology that we had developed for monitoring the strain in a fastener hole on an airframe for an airplane, to monitoring large deformation creep strain on hot gas path turbine components. And the rest is kind of history. GE bought the company. We went and worked there. My job was to, build a pilot program with the factory aerosol jet technology, and then we engaged with you guys, and we built a big bad robotic system that was highly flexible and capable of putting the sensors virtually anywhere on these very complex, massively heavy parts, which was, just an awesome project. As a 26-year-old engineer, to have the ability to design something like that, it was just it was awesome. And I got to meet you and your whole team and everything, and the rest is just awesome.
Yeah, you know what? That's a great example where without robotics, without 3D printing, that application probably isn't possible. Like, I've seen a lot of ceramic coating systems, and doing anything precise, precise was never in the equation, and when people talked about it. So was there other competing things outside of the 3D printing that could apply something to that accuracy?
Oh, yeah. I mean, absolutely. We looked into, welding features on. There were all manner of things, but when you start getting into the world of gas turbines, you very quickly realize that the designers of those parts, they don't want to put anything on them. They're designed for a performance capability, and when you put a bump on it, it affects things. You wouldn't think that,
especially in the gas path, right?
Yeah, I mean, you're talking about 50 atmospheres of pressure and a lot of heat and a lot of flow, and turbulence is the enemy. So it's just not only that, but then these are structural metal components that we're trying to monitor strain with. So if you go welding on it and doing all kinds of stuff, it's going to cause more problems than it's actually solving. So the ceramics were very nice because we could apply them onto the surface of the part. We could apply them without any intrusive damage to the underlying metal substrate, and the ceramics were designed for that purpose. So they survived in the engine, and getting the data out of the machine or out of the engine out in the field was, the unique challenge. And then storing the data and doing analytics on the data and trying to understand which parts are good and bad and doing different repair strategies to try and save money. All of that came out of that project, and I think was really wildly valuable. But without robotics, like you said, I don't think that we would have been able to put as many sensors on the part and as many unique locations. I mean, without robotics, just like you said, without additive manufacturing, without robotics, there's almost no way that we could have put those sensors on such a wide range of complex airfoil surfaces exactly where design engineering told us to. They're like, we want a measurement here. And we said, okay. And you just program it in the machine and it puts a sensor there. And, because we designed it for that level of flexibility and versatility. And that's the true power of robotics, not just for, material handling and those types of things, but the things that you can do with it at manufacturing implementation level, how complex of a process you can actually implement with what it enables you to do.
Yeah. So I love that example. And, when we start looking at the report that we shared together, it's a European Commission report from 2017. And then we also had one from 2020. So I like to do that where you look back in time and say, okay, what did we think was happening? And what do we think needs to happen in order to unlock the potential of these applications? So, for that application there, the merger of 3D printing and robotics unlocked being able to put those strain gauge sensors in complex places so that we could get more data and things can last longer in the field to save money on repairs, all that type of thing. Now, one of the common themes that has been talked about a long time, and it's common between robotics and 3D printing, is democratization. So there's a lot of effort, for example, in robotics, all the collaborative robots that are coming out. At first, it was thought that the benefit of those was because of increased safety around people, so people could work side by side. That was a benefit, but it's not what unlocked the potential and what the big wave is right now. The big wave right now is they're easy. So everybody can give it a try, experiment with it, and that's unlocking more applications, more ideas in order to try it. And what we see is, they get to try something, and that's great for the pilot project, but then they might go back to traditional robots for the real deal, right? So we see a lot of customers, they'll take a collaborative, try and polish something. It does it, but not as fast as a traditional, and in any ways, you might have some pinch points, so you can't leverage the safety. So when they go to industrialize it, then they ask for a traditional robot, and they put it in a cage with dust collection and stuff like that. So in the world of 3D printing, what's the democratization? What does that mean? Is that an important thing in your realm, or is it?
Yeah, absolutely. I mean, I think that when additive manufacturing kind of blew up on the marketplace about 5 years ago, everyone wanted it to be more than it really needed to be, right? I mean, if you looked at there were examples where people were like, well, let's print everything and, additive. Well, additive is a tool, just like CNC machines are a tool. I mean, every company in the world buys CNC equipment in order to make parts. And additive is going to become just like that. Now, there are some real hurdles that have to be overcome for additive manufacturing. CNC machining operations, sure, there are ever more complex versions of CNC machines, and you have, lathes and vertical mills and all these different types of things that are used to cut chips out of metal. And along the same lines, there are additive manufacturing technologies like powder bed and DED and all these different manufacturing technologies that all have their own little niche, right? The parts that you can make with powder bed, you can't make with DED technology. And the parts that you can make sometimes with DED, you can't make with pure powder bed. Or if you do, they cost 5, 10, 20, 30 times the cost. So I think the democratization really comes with the lowering of the cost of implementing additive for companies, but also these engineers understanding the increased design space that they have to be able to use it and implementing the correct technology for the application that's required. And until you start seeing, and you are seeing it, you can see companies like Proto Labs and what's the other one? I forget. But these industrial scale print shops where companies who don't want to invest the money in additive can go to these manufacturers, and they have all of the machines, and they'll pick the right one for the application and help you understand which part should be designed with additive and which one shouldn't. And I think that over time, additive is not going to be a new technology. It will be a service that you can order. It will be a machine that you can buy. Just like there are CNC machinists, there will be people who are experts in additive manufacturing in the trade level, and you will just start seeing companies implementing things like heat exchangers and components. It won't be this new whiz bang thing. It will just be a way of doing things, and the benefits that additive adds versus something like traditional CNC machining, the part cost savings, the ability to gain performance from designs that you can't make any other way, part cost reduction, all of these things, the ability to design a component on Earth and send it through email and have it designed and built on the space station, right? All of these things will lead to the democratization, I think, of additive manufacturing, where it just becomes so commonplace to come up with an idea, think of an object at the design level for an engineer, iterate very, very quickly, and implement something for a cost and with a performance capability that would never have been possible before it.
Yeah, no, I was just leading into, you were comparing between CNC machines and 3D printing. There's a bit of a competing factor there. Now, I was just talking with a colleague. We saw a LinkedIn post about the Fanuc Robo Drill, and they were doing a little bit of bragging, saying I think it was something like they were manufacturing on average, I think it was 6,000 a month. I might have the number wrong. And so we were talking like, how did the CNC world get to that maturity level, right? Because in the robotic world, you have a number of competing robots. Each one has their own software. And a way to talk to it and a way to program it. So if you're doing anything complex, it's hard to jump between robot platforms and you become dependent on one. Yeah. I think the closest thing I've seen to there's many companies that are trying to solve that problem. There's even open source initiatives, Ross Industrial, that is they have drivers for all the major brands of robots, and it's an open source platform. That's their kind of approach to democratizing. When you think about CNCs, G-code immediately comes to mind. And everybody, all manufacturing, they've got usually one guy in-house at least that can program G-code. Mm-hmm. Is there a similar type of approach? Is there a standardization happening in the 3D printing world?
Yeah, I think that there has been a quasi standard for a long time, at least for 3D part planning, right? The STL volume-based file where you've just got facets on the surface of an object, or there's no actual parametric data in the CAD file. You can send that to pretty much any 3D slicing software, packaged or otherwise, and make an object, right? And I think that there are some real limitations to that file format, and a lot of the industrial printer manufacturers are starting to catch on to that. And I just heard actually recently that there is design standards being written for additive manufacturing. So taking a traditional CAD file and making it into a 3D object. Now, where that really breaks down, I think, is in the fringe applications that are starting to emerge, like additive manufacturing electronics, where you've got 3D printing with electronic circuits either on the surface or embedded into it as part of the manufacturing process of the component. And that, because now you've got multiple sets of materials and you've got requirements for actual functionality beyond just mechanical strength and loading and things like that. That's where things start to break down. But I do think for making parts, the STL is going to go away eventually. They're going to have this new standard. I'm trying to remember what the end of it is, the file format. Maybe I'll send it to you afterwards and you can throw it on the screen or something. But there definitely is engineering standards that are driving this stuff now. And I think that a lot of what's doing it is that the majority of the applications for additive manufacturing, really at the manufacturing level to scale, are very applications like aviation components, flight critical aviation components, where you've got like the FAA, they have certification processes and all these different things. So driving standards is extraordinarily important in order to be able to make components that will actually be able to be used in the real world. And I don't know if robotics has that same problem necessarily, but I think that those are challenges that additive manufacturing has been facing, and they're in the process of overcoming.
Yeah, I think robotics, where we get into those challenges, is the minute you start altering a part. So the minute you start changing the shape or polishing a part and putting heat into it, then people look at it much more carefully. If you're moving a part from A to B, it's not such a big deal, right? Yeah. Just, is there any marks that you leave? What's the repeatability? Do I need to have a camera that finds the orientation of the part before I grip it? Things like that get asked. But once you start a process, then you get into that realm of, okay, so what am I doing to the part, and how am I controlling it? And you've got to start putting some infrastructure around your application to collect some of that data and show and analyze what you're doing, right?
Yeah, absolutely. I always thought it was kind of interesting, because the products, when I first met you, the products that you guys were selling were mostly blade profiling. And I think when I was at Power, you guys were doing a little bit of coating, TVC, thermal barrier coating, polishing and stuff like that. But I remember walking through that GE Bromont facility and seeing those robots profile the blades, and you were telling me like these guys can't basically design these engines or manufacture these engines without these robotic systems now, because you guys can profile the blades to an accuracy level that the human can't really create, right? Yeah. You basically, and I thought it was such a beautiful, to your credit and AV&R's credit, such a beautiful product implementation, because you guys have basically designed yourself into a space where you're needed, right? In order for them to extract more efficiency out of the engine, they need you.
Yeah, I'd like to take credit and say that we did that on purpose. But in fact, sometimes you get a little bit lucky. So, we see a lot of different applications come through, and, understanding the benefits you get from a properly profiled edge of an airfoil, we had no idea about that. But we did see the challenges if you face when trying to do it by hand. Putting some of those, they end up being elliptical edges. And we're talking a quarter of a hair width when you're talking tolerance band. So trying to do that by hand is a real challenge while being efficient and no scrap. So that for sure we saw in our customer. We worked really close with them, and it took a little while to get the first one in the field. And then once we had that proven, we started to understand a little bit better. What were the gains, and why were the designers so focused on those edge shapes? If you could imagine, just your car, and if your wheel is a little bit off balance, then you're going to feel the vibrations. And these jet engines, they spin much faster than a car, and they're pushing a lot more air through. So any imbalance in the system, and there's a lot of inefficiencies that come about that. So yeah, that was a great one for us. While we're talking about airfoils, the next section that report talked about was radical transformation of verticals. So the next application that you and I have been looking at is actually in airfoils and repair of airfoils. And what I'd seen in the past was people were trying to repair these airfoils using weld, or they would cut out a section and put a coupon on it, weld that coupon on, and then there was all types of work bringing it back to its near net shape, right? Mm-hmm. And what you guys came up with was a way to adaptively, you had a vision system involved, and I'll let you explain it a little bit better, but adaptively add material on there so it's a much more efficient application. You're putting way less heat into it. And then on the back end, when you start talking about finishing and where robots can fit in, our job was much, much lighter. So I think maybe you talk a little bit about what the value you saw and why you guys saw that as such an important space in transforming the repair and overhaul market.
Yeah. And, I have a little bit of a unique perspective on this because, I used to work at GE. And so I saw first, and specifically inside of their repair technology center of excellence, right, where they develop repair strategies and roll them out to the world. And, they're not the only ones who do this stuff, right? Optomec, company I work for right now, we sell these DED systems to everybody, Pratt and Whitney.
Wait a second. I got to ask, what's DED?
Directed energy deposition. So that is the, just like powder bed fusion, or FDM, fused deposition modeling. It is the acronym for powder fed laser welding, essentially. And we package that into 3, 4, and 5 axis CNC platforms. Sometimes it's an actual CNC platform. Sometimes it's just a large motion platform with both open and closed atmosphere. And that allows us to print portions of objects, existing objects, like adding a near net shape back to a casting, or printing an entire object out of whatever metal you can muster up. And the controlled atmosphere stuff is really enabling for titanium, which is reactive metal. So we can pump our entire volume down to less than 10 parts per million of oxygen and print titanium powder to make refinished titanium blades, to add wear surfaces back to their near net shape. And as you said, the DED technology, because it is a laser fed technology, we can ramp the power very quickly, and as a function of how much heat's actually in the part. So we can monitor and use it as a closed loop feedback. That's one of the kind of the other things that we do. And that allows us to control how much heat we put into the part, to build it back up to its near net shape with as little surface finishing needed as possible, to the point where grinding would actually be an enabling approach. Most of these technologies, if you use TIG welding, you've got a pretty thick bead, because you're building a lot of material back. We're not talking about a millimeter here. We're talking about an inch worth of, the top of a investment casted part or something along that nature. And that to do that precisely and consistently, again, with very low scrap and high yield, and with as little post-processing and as minimal residual stress as possible, that's the value of using DED for that technology. And back in 2018, Optomec made an acquisition of Huffman Systems, which is a 30-year pedigree of delivering DED systems to both the power generation and aviation MRO markets. So they had, systems all over the world, and it was a great synergy with our DED technology. And we're making those systems and shipping them around the world, and we're making a big push into aviation MRO as we speak. With COVID, it's created some complications, I think, for the whole entire industry. But we see our value statement, again, similar to what you said about the profiling, in the sense that we can refinish these blades. These are forged, sometimes very expensive castings that are already being welded manually, in a lot of cases by hand, and being able to increase the product quality of the weld, decreasing the chance of cracks and those types of things, but also decrease the amount of cycle time that it takes to do each part, and the consistency of the part is where the value statement is, and that's why we're pursuing it. So Optomec, I think, looks at additive manufacturing a little bit differently than other companies, in the sense that, GE and all these other companies, they make, ARC EBM machines and powder bed fusion tools that are able to be installed in any facility and do any task. And it's up to the customer to effectively define their use model for it. And that can become somewhat challenging. We have identified an industry where these parts are already being made, and we have a significant performance and cost advantage that makes it very simple for them to work with us on it. And that's the main reason we're pursuing the business in that way. It's not that you can't do traditional 3D printing with our machines too, because you can. It's just that GE and Pratt and Rolls-Royce, they buy a whole lot more equipment to repair parts than they do to 3D print parts right now, and that's the big benefit.
Yeah. And there's a lot of improvements that they gain by doing that. Like I've seen a lot of the TIG welded parts, and that compared to your process, it's night and day, and you bring it so much closer. And there's the way you're changing the part is how can you say it? It's less invasive. So the approvals, I imagine you have to go through a lot of approvals, but you're going to have a better yield with your process, is what I see. Have you guys ever been approached? One of the big deals with some of the robotic processes that we do, it allows some of our customers to, on some of the older manufactured parts, so you might have an aircraft flying for 30 years, and then there's performance improvements that they put into some of the engine components. Mm-hmm. Is that a big value add for you guys? It turned out it is for some of the robotic processes. But do you see customers, building into some of the old parts, performance improvements or different features, or to help with, efficiency gains and things like that?
Yeah. I guess the short answer is I don't really know. I can't really think of any specific examples of that, but I can tell you that we have systems all over the world that have been there for decades, and they've been doing a lot of repair work. And we get customers who buy new machines in order to increase their capacity, or some of them use that machine to do some development work, and they implement a new process. So I'm not going to say it hasn't happened. I just can't think of a specific example of that. But I would certainly think that the engineers at these companies that are spending the time qualifying new design components, they definitely do that. And I can think of one. Actually, I can think of one example of, it wasn't specifically DED enabled, but GE, when I was there, had their F series turbine. They sold it for a long time, all through the 90s, like their best selling product for the longest time. So there's this huge fleet of engines out there. And so every couple of years, they have to swap the components out in order to send them back for repair and remanufacture. And what they found is that there were repair processes, certain profiles that they could cut in, materials they could add for wear surfaces that would improve reliability, and maybe even allow them to up the firing temperature of the engine, which means that you can extract more efficiency out of it. So I definitely think that happens, all over the place. And third-party service providers that repair engine components and even the OEMs are always looking for ways to add value to the customer. And if they can charge more for repair and add efficiency, I mean, absolutely. I don't know if it's as prevalent in aviation, though, because of all the regulations. I mean, you'd have to fly a lot of hours and test those components, because the original parts have certs.
Yeah. And to me, that's where the democratization, one of our slogans is humanizing robotics. Mm-hmm. And, we try and make things easy, because for us to dream up an application like that would add that value, us doing that in the lab is pretty much close to nil. But put a system in the hands of a customer and make them better than us with that system, that's where those type of innovations will come from. So that's where I see the democratization and making things easy for customers. That's where that becomes super important, and you end up with pretty interesting use cases coming out of that we would never dream of.
Yeah, I mean, to spin off that a little bit, and we've attempted to get into it on our end, right? But and then there are other manufacturers making these things, DMG, Mori, and others, right? But this hybrid approach, right, where you've got additive manufacturing and CNC machining in the same setup, where you can take a block of material, turn it down to a certain portion, add material to it, and make it functional in ways that would require multiple steps, if not multiple setups, in order to create the same functional part. And I think that the adoption of that has been maybe a little slow for whatever reason. And I think that our approach really, which is to try and get it into the hands of the CNC machinists, so that they understand when they look at a part and they think, okay, well, I need this much stock, and I have to cut these portions off, and I have to have this many setups in order to create this profile of this part. Well, if you give them the tool that says, okay, you can use half the amount of stock and 2 less setups by, printing this portion of the part, that is a design thought process that I think is going to take a little bit of time. But I think that right there will democratize the DED a little bit more, because just like you have small machine shops with CNC machines, you could start seeing small CNC machines shops that also have additive in them, and they're able to have that functional design space that currently is not enabled any other way.
Right. Yeah. So taking steps forward, you talked about some of the challenges there. So in the report, their major headlines were price, standardization, IP protection, training and expertise, quality versus speed trade-offs. So I mean, you touched upon a few things there. You talked about the training and expertise is a big one to, unlocking some of these use cases. Today, 3 years later, what do you see as, the next 5 years? What's important for 3D printing? And also, we talked a little bit offline about, what robotics can bring to 3D printing. What do you see as important things to work on over the next three to 5 years?
Yeah. I think that it's a little bit different for every technology, to be honest, and for every application. I mean, if you look at additive manufacturing for, I don't know, something like aviation versus oil and gas, right? The size of the parts, the complexity of the parts, the regulating requirements, the number of components produced per year. So, you talk about speed, are all different. And the commoditization of the cost is also different. So I think it's really hard to say, this is what's going to happen in the next 5 years for additive. But if you were to hone in on something like aviation, right, and you think about, okay, well, we're gonna what on the new make side, right, new aviation components. If they can additively manufacture a portion of the engine, like the GE LEAP fuel nozzle is a perfect example. Everyone can go online and look at what that nozzle was able to do. But that was a part that really couldn't be made any other way other than with additive. And the fuel savings that it benefited from are immense. And if the aviation industry hadn't been hamstringed by COVID, the adoption of that engine would have been massive. So if you think about the logistical nightmare of, okay, it was a new engine, we were making 2,000 units a year. In 5 years, GE wants to be making, 50, 100, 200% more. The number of machines that it takes to make those components, the level of inspection technology and surface finish technology, and all the stuff that goes along with that, just to make these small batches of components, to scale that up. With CNC machining, there's rules, there's standards. This stuff exists. They don't really have to go and figure it out. Additive is still figuring that stuff out. And I think the scaling problem is the biggest part of it. Where I think robotics plays a big role is in the material handling side of things. If you look at something like powder bed fusion, where you've got a build area that's X by X by X, it can make so many parts in a 72 or a 5-day build or something like that. How do you get those parts out through powder reclamation, post-processing, cleanup, inspection, all of those different things? Well, if you have a machine, maybe you have 3 or 4 or 5 machines that finish a job every 5 or 6 hours, and you've got a robot that's feeding X number of machines to do all of these operations that humans are normally doing, but in a very consistent manner with no health and safety exposure, with volumes that actually will enable these companies to make money. I think that's where robotics really plays in, because it's augmentation, process augmentation, where the robot is either doing material handling or specialized operations that would normally be done by a human being, and doing them in a very consistent 24-hour lights out fashion, so that you can scale the process. Because almost every additive manufacturing environment that you go into, you'll have banks of machines, and especially for powder technology, you'll see guys in these suits that have to go in there and vacuum out with an explosion-proof vacuum all this powder, and then there's these EDM operations to clean the parts up and all that stuff. And I think that all of that could be automated for certain applications that require high volume, and really help it scale.
Yeah, I guess, when you think about it, you have a 3D printing machine. When it's set up to hit go, the printer bed, everything is in shape. It does its job. It prints the part. Then there's a bunch of operations to get it back to the original state, right? So you got to remove the part, got to clean up the bed, you've got to reclaim the powder, you got to treat that part. So that's the focus area that you see post printing, where there's a lot of work to be done with automation still.
Absolutely, and I think that you're seeing that even right now with CNC machines. I mean, using a robot to feed material into and out of a CNC machine with automated tool changing and fixture changing and those types of things. Not a big deal when you're talking about parts that fit in your hand, but when you're talking about really big parts that require cranes and large men with highly specialized equipment in order to move those pieces in and out. You look at some of the robots that Fanuc or KUKA makes that can lift a car and whip it around at a meter a second. That is really enabling. It allows you to scale the process in a way that human beings just can't do it. It's efficiency gains, and enablement, I think, from a manufacturing perspective. And additive is no different. I mean, the fact that robots don't get sick when they get exposed to metal powders, and that robots can load components in and out of machines in a very repeatable fashion, and you can program robots to do multiple tasks that all take different amounts of time with sensors and things like that. The productivity gains associated with being able to do that are just they're no brainer. And I think that pretty much any highly scaled additive implementation where they're making tens of thousands, hundreds of thousands of components a year for real production, robots have to be there, because human beings just will not be able to sustain that level of efficiency and work and precision and even safety perspective that's required for these types of applications.
Now, you talked a little bit about surface treatment of parts as part of that value chain. What are the big hitters? So you talked the gate cutoff or the connection cutoffs. What are the polishing or sanding? What are the major finishing or surface treatment processes that you commonly see?
Yeah, well, I mean, I guess the question always becomes, do you need surface finishing or not?
Yeah, okay.
So finish machining for exterior surfaces, ceiling surfaces is, the most straightforward, right? You print the part, the internal cavities, the external cavities are near cast finish. And then you finish machine the parts that have to interface with other components or bolt on to things. So that's the first one. I think finish machining and leaving that as cast finish or near finish is good enough. I think the laser technologies and the powder technologies are going to continue to get better. And just like you see, FDM and laser curing machines able to produce parts where you can't even see the layers. I think the powder bed technologies are going to get that good, but they'll be slower and more expensive, and the powders will be even harder to deal with. So there are finishing technologies out there, microabrasive, flow-based ones where they, push a material through continuously and it chips away at the walls, or you put it in basically a rock tumbler to, create, mirror quality finishes where, you go from different size media progressively down. And all of those approaches are viable depending upon the application. So I think you're going to see you already are seeing companies pop up that offer those machines that do that, those services to, they're building those services into the additive manufacturing process. At least for metal components, that's kind of what I see. For plastics, I think that we're going to start seeing, I think we already are seeing injection molded quality finishing from plastics. And we're going to start seeing engineering grade, even composite materials with that same level of quality. I mean, I watched a webinar the other day. There's this company called Fortify. Everybody can go look at them. But, they do photonically cured polymeric materials that have, fibers and things like that. They give them the isotropic material properties of traditional engineering grade plastics out of a stereolithography or digital light projection based printing technology, which traditionally doesn't have that. And that is wildly enabling that you can create, all the benefits of 3D printing with all the benefits of modern injection molded plastics. That's like I think it's going to be huge. Speed will always be a problem, right? Injection molding is so fast, but for certain applications, it's going to be a game changer for that, I think.
So closing the loop here a bit, when we go back to, the first application we worked on together, we had a big part. And so we had the aerosol jet printing system. We had a robot helping manipulate this big part. And, often I see, there's certain enabling technologies that a robot brings versus a CNC, for example. Like anytime that you want to have apply a force against a part, a robot's really good at measuring that force and compensating. Anytime that you want to get into some machine vision, it's a much more flexible platform to use that on. Occasionally you see robots actually doing the 3D printing as a motion platform. What's limiting from your view right now? Like what would be the benefits of a robot? I can see maybe the flexibility and when you get in a finishing system, when you get into some of the larger parts and you have some more tricky features to get into, a robot is just much more flexible than a CNC machine is, but it's not as accurate. So you got to do other tricks such as force feedback or compliance to get around that. Do you see a future where robots will be used more for the motion platform?
Oh man, I hope so. I think that the flexibility that robotics brings, almost every single operation that you see for additive that involves a robot, the robot's loading the machine. And it's a little frustrating because you have this highly flexible 6-axis robot that has more than enough travel and flexibility in order to be able to apply the material, but you need the precision of the CNC machine with its encoders and its linear rails and its setup precision in order to get that level of accuracy in the component. So I do see huge benefits of being able to use robotics in ways that other than just material handling, where they're actually doing the motion. I mean, think about how much a machine costs to have a CNC machine plus a robot versus just a robot with a print head. I mean, and also all of the benefits that come with loading and unloading and things, especially when you start talking about in our world, which is controlled atmosphere, right? I mean, getting a batch of parts into and out of a 10 ppm of oxygen environment is not a trivial thing, and there's almost nobody that does it other than us. So it's hard, right? I do think that the robotics are really enabling. Where I think they fall short is, like you mentioned, on the accuracy side of things, specifically with respect to Cartesian motion. I think that if robotics could find a way with their multi-joint 6 degree of freedom to have more precision in specifically the XYZ Cartesian motion, I think we would probably start seeing a lot more use cases where 3D printing could do the work. So, and I think there are robots out there, right? I mean, look at the little Mechademic 500. I mean, that thing has, sub 5 microns of positional repeatability. That's wild.
Yeah, that's probably the most accurate one that I've seen to date. And you're right, that one is pretty interesting. One of the things that I'm seeing a lot of is there's your robots are getting mobility now, so you're starting to see a lot more applications where you can mount a 6-axis arm on top of one of the warehouse robots, and it's able to roam around. But when you start to pull the hood off the cover, some of the path planning and navigation tool sets that are being built, and when they start using that in different ways to give feedback to some of the Cartesian systems, you can start having a tighter feedback loops. And I'm wondering if that will unlock some of the more precise applications as we go forward, as opposed to there'll be the hardware side, but I see that as potentially a software component that could be quite interesting.
Yeah, no, absolutely. I think that, all of the things that you guys integrate into your systems, like laser distance sensors and laser profilers and 3D scanners and vision systems, those feedback mechanisms work just like the glass scale encoders on our aerosol jet machines, right? They update position and they can update position in real time, or provide feedback for you to be able to manipulate path planning with respect to software. And I think it all really comes back to what the application requirements are. If the application requirements, need 5 microns worth of, XYZ positioning accuracy and, sub 50 arc seconds or something like that along of, orthogonality between those Cartesian axes, you just, the robot can't do that with the closed loop feedback mechanisms that it has today. So new ones, I think, would have to be developed. But there are applications like what you guys do with profiling, right? You pick up a part, you scan it, and then you basically write a custom program for that particular part based on what the actual edge profile is and the force feedback from the component. And I'm sure that you didn't get it right the first time. It took thousands of iterations to figure out how to modify that motion code in order to get the profile. And I think that there are people who are playing with robotics in those ways that will be wildly enabling. But it's there's really not a whole lot of substitute to a CNC machine for many applications. And it's an incumbent technology. It's relatively cheap to implement. You can get them from pretty much anywhere in any size you want with whatever level of accuracy you need. But robotics enable some implementations that are just hard to ignore, for sure.
Yeah, absolutely. I think they're complementary in more ways than they're competitive. So I think leveraging the strengths of the two is the way forward until we figure out some of these other things.
Yeah, I would agree with you.
So Bryan, we're right at the end of the hour that I have with you. So it's been a pleasure having you on the show, and I really appreciate your insights and your input here.
Hey, no problem. Thanks, Mike. This was really fun, and I hope we get to do something again soon.
Yeah, once you get yours launched, your podcast launched, make sure I'm on your show list.
All right, you got it, man.
Right on. Thanks, Bryan.
Bye.
Bye. So this concludes the episode of Robotics for All podcast by AV&R. If you don't want to miss another single episode, don't forget to subscribe to our show in your favorite podcast app. Thank you very much, everyone, and we'll talk again soon.